Routing and Switching Essentials, Chapter 6, Static Routing. Alright, so what exactly is static routing? That's the focal point of this. We're going to talk about implementation, we're going to talk about how to configure it, plus default routes. We're going to do a review of our CIDR and variable length subnetting. We're going to talk about how to configure summary and floating static routes. Lastly, we're going to talk about troubleshooting static routes, as well as troubleshooting default route issues. Our main objective is to explain and look at the advantages and disadvantages of static routes as opposed to dynamic routing, explain the purpose of the different types, look at how to configure both IPv4 and IPv6 routes, how to then configure those routes, explain the use of legacy classful addressing and network implementation, and explain what a CIDR is. We're going to also talk about design and implementation for our address schemes. We're going to talk about how to create floating static routes to provide a backup connection. That's always a fun one. We're going to discuss how a router processes packets, and we're going to end with some troubleshooting. So, reaching remote networks. We can reach a remote network or a distant network one of two ways: manually, also known as statically, or dynamically, which is dynamic, learned. Manually, remote networks are manually entered. You have to statically assign them. Dynamically means they can be automatically learned or dynamically learned via a routing protocol. So why use static routing? Some of the advantages: static routes are not advertised, so they can lead to better security. Static routes use less bandwidth, also no CPU cycles. And the path to a static route to send data is known, meaning if you want to go from A to B, C, D, the paths between those locations, they're known. They're manually entered, so there's no guesswork. You know exactly how they're going to get there. With dynamic, how communication will flow from A to D, that will depend on the topology and current circumstances of that routing cable. So the pathway is not known. There are some disadvantages. The initial configuration as well as maintenance time. That's huge. We have to set it up. Also, setting it up could also be error prone. Larger the network, more errors can occur. Administrative intervention is required to maintain the route information, meaning as we add additional routes, an admin has to go around and update everything. It doesn't scale very well. And you're going to have to know complete knowledge of the overall network every time you reconfigure. So the next normal question is, well, when do we use a static route? Static routes have three primary uses: provide ease of routing table maintenance, and smaller networks. Routing to and from stub networks. Now, a stub network is a network accessed by a single route, and the router has no other neighbors. And that's pretty common for most small networks, even some medium networks. Most of the time, we are going to be forwarding everything to an ISP, so we don't have any neighbor routers locally. Using a single default route to represent a path to any network that does not have more specific matches with another route in the routing table. Default routes are used to send traffic to any destination beyond the next upstream router. We're going to explain that here in a little bit. Static route applications. Static routes are often used to connect a specific network, to provide a gateway of last resort for a stub network, to reduce the number of routes advertised. That could also be by summarization, helps with congested networks, and create a backup route just in case a primary route goes down. Here's an example. R2 is our only neighbor, is our only pathway out. So 172.16.3.0, the /24, that is our stub network. There is no point in using a routing protocol because everything that's not internal to R1, we're forwarding to R2. Doesn't matter what it is. A default static route is a route that matches all packets. A default route identifies the gateway address to which the router sends all IP addresses. A static route normally is a 000/0 interface or address. Those are specialized addresses that's going to match any IP with any subnet, and it's going to forward it out a specific interface or address. We're going to get more into that when we do the configuration portion. Let's talk about route summary. So generally, route summary, you take a list of networks, 172.20, 172.21, 172.22, 172.23. And what you do is you figure out what's the common or the commonality between all of them. What bits are the same? Going from left to right, we figure that out. And the second we start getting different numbers, we know that that's not a summary address. So if you do always see the first octet 172 is the same in all of them, that is a typo. In the second octet, 20, 21, 22, 23. Okay, so there is all of the numbers broken into binary for us. And we're going to notice that those are the bits. That way are the common bits. We have a 0 in the 128 spot, a 0 in the 64 spot, a 0 in the 32 spot, a 1 in the 16 spot, a 0 in the 8 spot, and a 1 in the 4 spot. The common ones, all of them have in common are 0, or is 20. They add up to 20. So everything to that side, we're going to change it to 0. So that is how we get our 172.20.0.0. How did we get the slash number? Okay, here in the 172 in the first octet, there's 8 bits. They're the same all the way through, so we're going to keep those 8 bits. Here's 9, here's 10, 11, 12, 13, 14. So there are 14 bits that are remaining the same between all of them. That is how we get the 172.20.0.0/14. And that is the start of route summarization. So that's the beginning of at least route summarization. So let's go ahead and move on to our floating static route points. So a floating static route are static routes that are used to provide a backup path just in case the primary route goes down. Now that primary route could be static or dynamic. It's just a way that there's a secondary path to choose from. Floating static routes are only typically used when the primary route is no longer available. So to accomplish this, the floating static route is configured with a higher administrative distance than the primary route. That way, what happens is the lower administrative route is the primary route. When that route no longer becomes available, it will see if there is another route possible, even if it's a higher amount, and it will then take the primary role. So let's get into how we set up our static routes. How we do that is from global configuration mode, we type IP space route, the network address, the network subnet mask, and either the IP address to the next hop or an exiting interface. So the network address, that's going to be the network ID. The subnet mask will be, again, the subnet for that network. The IP address of the next hop, or an exit interface. The next hop route, only the next IP should be specified. Directly kinetic static routes, only the router exit interface should be specified. A fully specified static route, which again should also use the next hop address or an exit interface. That way, you can, if you want to control specifically a fully specified static route, you want to tell things exactly how to get from A to B, you can use a fully specified static route. Example, if we want to go from PC1 to PC3, you can tell it forward everything from 172.16.3.0 with a subnet of 255.255.255.0. Send it. And you could either do the exit interface, so that interface, or you can give it that IP address. And for static routes, if you want to be specific, you could give all of the different networks. So for router 1, you could actually set those 3 addresses on router 1 so that router 1 knows to forward any address matches of those out that interface. On R2, you would just need those 2 routes. And what you do is you tell router 2 IP route 172.16.3.0.255.255.255.0, send out that interface. And anything for 192.168.2.0, 255.255.255.0, send out that interface. And lastly, on router 3, you'd set those 3 routes. Because again, the router knows what's directly connected to it. So router 3 knows these 2 addresses. So you just have to tell the router 3, the routes that it doesn't know about. The question here is for R1. R1 must know or determine how to reach 172.16.2.2. And it knows that because it is directly connected. If R1 needs to know how to connect to 172.16.1.1, R1 currently doesn't know. That's why we have to use static routes or a routing protocol so that they know how to get through. And here we go. It'd be IP route, and you'd be assigning the other routes that they don't know about. You can set it to go out an interface, or you can tell it the next hop. That interface right there, 172.16.2.2. In a fully specified static route, both the output interface and the next hop are specified. That way we can be very specific. This is another type of static route that are used in older iOSs prior to Cisco Express forwarding. This form of static route is used when the output interface is a multi-access interface, meaning has sub-interfaces. To verify a static route, we could be looking at show IP route static, or show IP route with the network command. So how could we set a default static route? That will be IP route 0.0.0 space 0.0.0.0. And then you either give it the next hop or an exit interface. Again, this is code. Any IP address with any subnet, send here. Okay, so what we can do is we can tell it send everything from our LAN to 172.16.2.2, and that will forward it that way. That means any IP address of any subnet received on this network, we're going to forward out that way. That's not specific, but it would work. Same thing here. We could do the same thing sending it that way. However, R2 don't have that option. You're going to have to be specific on the routes it's going to send. Alright, so how do we verify? That's always a good one. So verifying a default static route, that will be a IP route. It will have a S static. So now we talked about setting up IPv4 material. How do we do IPv6? And there are 4 types. There's a standard IPv6 static route, a default IPv6 static route, a summary IPv6 static route, and a floating IPv6 static route. Most of the parameters are damn similar. The key thing here is IPv6, route, the prefix. However, this time we can do the slash notation. Example would be FE80/64. We can now use the slash number here. And you have to tell it either the next hop or the next interface. Pretty similar to, again, IPv4. Standard, default, summary, and floating. Same general explanation for IPv4. You just have to remember that here we're using a separate IP version protocol. Next hop for IPv route. That's, again, it's going to be the next IPv6 address. Directly connected, fully specified static routes. Again, same thing like IPv4. The difference here is IPv6 route, the numbers are going to be different. Instead of using an IPv4 in dotted decimal form, we're going to be using a IPv6 with slash notation. That's really the difference. Same thing, except this is going to be a static route using an exit interface instead of a specific IP address. Configuring a fully specified static IP route. What you can do is you can tell it IP route 2001 DB8 ACAD:2. That's DB8. That's going to be right on this side of the router. You're going to tell it send this network out that interface to that IP address. That tells it the exit interface. That tells it where is it going. And that is a fully specified static route. How do we verify? How do we check? We can use show IPv6 route, show IPv6 route static, show IPv6 route with a network address. So, how do we set a specialized default static route? Before we were using zeros. Here we're doing pretty much the same thing. IPv6 route ::/0. The colons represent all leading zeros, or all the zeros, /0, any subnet, and out one of these interfaces. Here's another example of an IPv6 route with any address. So it's going to take any input from this side, and it's going to funnel all of it to this IP address. So regardless of the IP address, it will forward it out to R2. Here we can see a static address, and that is the basic of static routes. So let's go back a little bit to our IPv4 fundamentals. Let's talk about classful network addresses. Classful, class A, B, C, our multicast, and our reserve. So our class A, the leading 0 or the leading bit will always be 0. The class B, 10, class C, 110, and so forth. That's because our class A is between 0 and 127. So the first bit can never be 1. The start and end bits for class B, same thing there. We'll always start with 10. For class C, always 110, and so forth and so forth. Our multicast will always start with 124.0.0.0 and give you that range. It will always start with, in the first octet, 1110, and the rest of it can be different. Okay, so pretty straightforward stuff. This is all basic IP addressing again. Class A, 255.0.0.0. That means only the first octet's locked in. The rest are hosts and can be changeable. Class B, the first two are network, and the last two are hosts. Class C, first three are network, the last one are hosts. Meaning we can manipulate the hosts. We cannot change the network portion. And so that's exactly why class systems didn't last very long. We were being locked in, even if you only needed a few addresses, you were being locked in with hundreds of thousands of addresses, or 65,000 addresses, or 250 addresses. So you were limited. Those were not true numbers. For a class C, it's 254 usable. For class B, it's 65,000 addresses, I believe, and some change. Class A, we're talking millions of addresses. So a classful routing protocol. You could not separate them based off of our class separation. Because class B would be 172.16. That's why these can be separate. But if we wanted to manipulate the second octet, it wouldn't work. These were fixed length addresses, and they're not very good. So we wasted a lot of addresses. So class A would give you roughly 126 different combinations, so 126 different networks. Each of those networks allowing for 16 million hosts. A class B, you could have over 16,000 different combinations, but each of those combinations, each one could be limited to 65,000 and some change. Class C, we could have 2 million different combinations, each combination consisting of 254 usable. Again, that was wasteful. This is the breakdown. This is very wasteful. So classless came in. CIDR equaled more efficiency. Became more efficient. We broke our classes and we said we can change them to whatever we needed. Let's go back to our CIDR and route summarization. How could we summarize 192.168.0, 192.168.2, 192.168.4, 192.168.8? We could summarize them in a 192.168.0.0/20. Because again, you break all of these down to binary, and you see where everything is the same. Here's another example. All of the different routes here are summarized in 192.168, are all summarized in 172.16.00 with a subnet of 255.248.0.0. Again, we're just taking where things are always the same And to the left of that, we're counting how many bits there are. To the right of that, we're changing them to zeros. Classless routing protocol example. We can have different classes. We could have variable length subnetting so that while they're all separate networks, like here, the first two octets would normally be locked in. But here, because they're classless, we don't have to follow the classful addressing scheme anymore. So let's look at fixed length subnet masks. We're going to look at where everything is the same. Here, the first three groups are the same. Only in the fourth octet do they start changing. And even here, we could summarize these two groups, these three groups, because they all start with zeros. So we could summarize them that way. If you didn't want to do that, we could summarize these guys by the first zero. If you didn't want to do that, we could summarize with just all of these being zero. So it would summarize here. All of those turn to zeros. All of those are locked in. And that's a simple way to look at summarization and fixed length subnet masks. Here we could do variable length. We can start changing it up. What are our requirements? What do we need? I've already done numerous videos on subnetting. So for the nitty-gritty for subnetting, double check those videos. Variable length subnet masks in action. They allow us to manipulate the network how we need to. Basically, it is simply subnetting a subnet. We can group our subnets how we need them to be grouped. Here we can segment them into one network, and then we can segment them again based off of our requirements. Here we go. If we were doing a fixed sublink mask of a /27, our grouping would be an increase by 32. That's why from building A, B, C, and D, the increment is 32. But we do not want to assign 32 addresses down here. Here we want to assign a /30. That way we only have 2 usable addresses. That is okay. That right there is the power of variable length subnetting. So CIDR is a form of route summarization and is synonymous with the term supernetting. CIDR ignores the limitation of classful boundaries. Throw out the idea of classful. This type of summarization helps to reduce the number of entries in a routing update. Calculating a summary route, again, we see where things are similar. This is where they're all similar. We draw a line. That is our summarization. You count how many bits there are. All of those change to 0. And we get a 172.2000. Because these equal 172. These equal 20. All of these equal 0. And on this side, there were 14 bits. Summary static route example. Again, same thing we've been doing. We see where they're the same. We draw a line. And here is our new subnet mask. All those turn to 1s, all those turn to 0. That way we get our subnet mask for our summarization. Aside from the fact that IPv6 addresses are 128-bit and in hexadecimal, most of the same concepts apply. Multiple static IPv6 routes can summarize into a single static IPv6 route. Same thing with IPv4. Calculating IPv6 network addresses. The general steps: list the network addresses and prefix. Identify the parts where the addresses differ. Expand IPv6 if it's abbreviated. Convert from hexadecimal to binary. Count the number of far left bits that are matching. Then summarize. Copy the matching bits. Change everything to the right of that to zeros. Convert the binary back to hex. You're good to go. Again, just like we did in binary summarization or IPv4 summarization. How do we set up an IPv6 summary address? Just like we set up an IPv6 route. This will be a summary address. Floating static routes are static routes that have an administrative distance greater than the primary one. Same thing that we've done with IPv4. But now we're going to show you how to up the administrative distance. Here we have two static routes, this guy and this guy. Notice the second route has 5. You can always do space and a number, and that will be the administrative distance. That way, it will use the first route possible. If that's no longer possible, the second route will come into play. And it has a higher weighted administrative distance, so it will only be as a backup. Testing the static route, you can do a show IP route, trace route. You can always shut down the primary route and redo IP route and redo trace route to verify. The last thing we have to talk about is troubleshooting. So how could we start troubleshooting? How could we troubleshoot static routes and route or packet forwarding? Our big commands are going to be ping, trace route, show IPv route, show IP interface brief, show CDP neighbor details. Do not forget the specific show commands for IPv4 and IPv6. These are things that you're going to want to learn because long term, they help you. They help you troubleshoot routes if they're missing or not. Solving connectivity issues. Find a missing or misconfigured route is relatively straightforward. You slowly start pinging. You ping your default gateway. You ping the next address. You ping the next address. You start seeing where the route no longer is allowing communication. That's where you start looking. Here, from PC1 trying to ping PC3, I would try pinging PC1 to PC3. If nothing happens, what I would start doing is, from PC1, can I ping here? Alright, if I can, good. Can I ping here? If I 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 can, try to ping here. You slowly walk down to see where you can ping. Wherever you can no longer ping, that's where you know, hey, I need to see what's going on there. If you cannot ping, slowly walk through them. This is exactly what I just did, but in straight detail. Slowly walk one route one interface at a time, one route at a time. That way you could see where the communication problem is laying. That's actually all for Chapter 6. There's a lot of good material here. The important one to take away. Static routes are great, but can be a really big pain in the butt. Second, the admin distance for a static route is 1. That's a good test question. I wanted to thank you guys and hope you guys have a great day. Bye.